Okay, hello class. Now we're going to start moving on to section 2.4. Okay, and this is on what we call infinite limits. Infinite limits basically give us the case, or it's us analyzing what happens when, say, we try to plug in the value and instead of getting 0 over 0, we get a constant over 0, right? This is the constant over 0 case. This is basically a case where we can't really factor. I mean, the example we're going to look at here is we're going to start with the right-sided limit. The limit as x goes to 0 from the right of 1 over x. So if we just plug in 0 into x, what happens is we end up basically getting 1 over 0. Okay, this isn't a 0 over 0 case where we can just kind of factor and cancel or use a conjugating factor or whatnot. We have to do something else. Okay, so I have a table set up here where I have x, of course, and 1 over x. And look at x's as x gets closer and closer and closer to 0 from the right. So we start at 0.01. When we divide, right, we get 1 over 0.01, which gives us 100. Moving along, 0.001 gives us 1,000. Plugging in 0.0001 gives us 10,000, and so on. And as we see here, as x gets smaller and smaller and smaller, or as x gets closer and closer and closer to 0, okay, 1 over x gets arbitrarily large, right? So it gets just as large as x gets small. So as x goes to 0, 1 over x increases without bound, is what we say. Okay. So I have this sort of written down here that, right, as x gets arbitrarily close to 0 from the right, 1 over x is getting arbitrarily large. As x gets smaller or closer to 0, 1 over x gets even larger and larger, just as large. So, what we say is that in that case, the limit as x goes to 0 from the right of 1 over x is infinity. Okay? Basically, it's increasing without bound. That's what infinity means. Okay? On the other hand, if we check from the left, right? So now we're looking at the limit as x goes to 0 from the negative side, and we get basically the same numbers in our graph, except we get negative numbers, right? We're plugging negatives into 1 over x, so we get negatives popping out, right? So, looking at this table, we see that as x gets arbitrarily close to 0 from the left, 1 over x is not actually increasing without bound, it's decreasing without bound. Okay. And what we say there is basically 1 over x is going to negative infinity, right? Going down to negative infinity. So what actually happens, right, when you have a constant over 0, it's basically always going to give you a plus or minus infinity, right? That's a blow-up point of some kind. Because a 0 over 0, things could actually cancel. But 1 over 0 or 10 over 0, things aren't canceling if it's in its most simplified form, meaning that it has to be a blow-up point. As the numbers you're dividing by get closer and closer and closer to 0, they basically flip, invert, and multiply to become larger and larger and larger numbers, right? So it turns out to actually be, as you divide closer and closer to 0, you actually end up multiplying by larger and larger numbers. Okay, so what this boils down to is once we see that we have a c over 0 case, it's all about trying to see which one it's going to be. Is it positive infinity? Is it negative infinity? You know, on which side is it going to which? Okay, so I have the graph of 1 over x here. We can see that. It's kind of big. Kind of big, but as we see here, as x gets closer and closer to 0, the y's are getting arbitrarily large until finally they're just going right off the page. Okay? So as x goes to 0, the y's are going up to positive infinity. And on the other side, consequently, I'll do this side in red. As x gets closer to 0 on this side, right, the y's are shooting down until eventually about right here, we're already off the screen. Okay, we're off the page. So here, as x gets closer and closer to 0 from the left-hand side, the y's are dropping down to negative infinity. Right? This is what's going on at a constant over 0 case. Right? This is what happens when you divide by 0 in such a way that things don't cancel. Right? So this is division by 0. Okay. All right. There's another. One last thing I wanted to say about this. What we have here is, right, the limit as x goes to 0 from the right, 1 over x is infinity, and the limit as x goes to 0 from the left of 1 over x is negative infinity. That means the limit as x goes to 0 from both sides is obviously does not exist. Now this is very kind of subtle. Officially, infinite limits don't exist. Okay, so officially, when the limit as x goes to a of f of x equals positive or negative infinity, right? This is a form of does not exist. But it's a very special kind of does not exist. It's a type of does not exist that we can actually talk about what the function is doing. We can say, hey, it's shooting up to positive infinity, shooting down to negative infinity. We have a blow-up point. All right, the function blows up in some way. All right. Okay. So it's a subtle thing, subtle type of does not exist, but it needs to be mentioned all the same. The next case is actually, messed that up there, but now we're going to look at the limit as x goes to 0 of 1 over x squared. Okay, so here we pretty much are doing the same thing. I think, I'm not sure if this is absolutely correct with the zeros, but the idea remains the same. Basically, as x gets closer and closer to 0 from the right, 1 over x squared is increasing without bound, and it's going to be increasing without bound even faster than 1 over x because we're squaring. But the difference here, okay, is that from, I think I misspoke here, this is from the right. From the left, so negatives, right, we're also getting positive values here because, well, the x squared is going to make those values positive. Okay, and again, like there needs to be an extra 0 there. So what we basically have is the limit as x goes to 0 from the positive side of 1 over x squared is equal to the limit as x goes to 0 from the left, or from the negative side, 1 over x squared, and they're both equal to infinity. So in this case, we can actually say the two-sided limit as x goes to 0 of 1 over x squared is infinity. And here's the difference here. When we look at the graph, we see that on both sides, right, on both sides, the function shoots up to infinity at 0. Okay, from either side. So it is possible with constant over 0 cases to have the two-sided limit actually equal infinity. Still doesn't exist, but all that means is that the function goes to infinity from both sides. Okay, so let's look at a graphical example here. This one's kind of big, but it fits well enough for us to see what's going on. And I'm going to look at the limit at each little particular asymptote. Okay. So let's look, shift this over, let's look at the limit as x goes to 3 from the positive side of f of x. Right, so we're calling the graph of this guy f of x. So these are just the axis lines, by the way. So when x is going to 3, okay, from the right, we see that, well, the function itself is doing what? It's shooting up to positive infinity. Okay, and what is it doing from the negative side? Notice I don't just write the limit all by itself. I always write the limit with a function. Okay, so from the negative side, remember, 3 is what we're looking at, and we're coming at it from the negative side. So when we map these values up, we see, oh, hey, the function is shooting up to positive infinity. Okay. So the limit from the right and the limit from the left both equal infinity, so we can actually say that the limit as x goes to 3 of f of x is positive infinity. Okay, that makes sense. At 0, the graph, right, is on both sides going up to positive infinity. Right. So next up, we'll look at 1. So how about the limit as x goes to 1 from the right? Okay, so here's 1. And I'll do this part of the example in red. So there's 1. And from the right, from the positive side, we see that the function is here and going up to positive infinity. So the limit as x goes to 1 from the right is positive infinity. On the other hand, the limit as x goes to 1 from the left, well, when we look at this side of 1, to the left of 1, each tick mark that gets closer and closer and closer, well, that is actually going down to negative infinity. Okay, shooting down. So really, think of a limit as I'm starting maybe halfway away from, say, 1 and heading towards it. What is this graph doing? What is the roller coaster doing? If this were a roller coaster that we were riding along, well, we'd be shooting down to infinity, or excuse me, negative infinity. All right, and since these two-sided limits here don't match, from the right it's positive infinity. From the left, it's negative infinity. So from both sides, well, the best we can say is that it does not exist. Okay. So see if we can follow along here. The limit as x goes to -3 from the positive side, f of x, what is that going to be? And I said -3, it's actually -2 I want to look at. Okay, so -2. Okay, from the positive side, from the right, everyone see that it shoots down to negative infinity? And what's it do from the left? Well, from the other side, it's going up to positive infinity. So what could be said about the two-sided limit? Does not exist again. Does not exist. Okay, the next thing I want to talk about real quick is a new definition. Okay, a new definition for vertical asymptotes. If you remember back in pre-cal or your algebra class, you're probably told that a vertical asymptote was just where either you had division by 0 or where the graph blew up, right? Well, now that we have limits, we have a better way to actually define these. What we basically say is that if the limit as x goes to a of f of x equals plus or minus infinity, okay, or it doesn't have to match. It could be the limit as x goes to a from the right or from the left. They don't even have to match. If one could be positive infinity, one could be negative infinity. Either or, doesn't really matter. If that's true, if one of these is true, then we say that f of x has a vertical asymptote at x equals a. Okay. So that's an important way to talk about asymptotes. So we would say that this graph here has vertical asymptotes. We often just put VAs. Well, at -2, so we actually have to write x equals -2 because it's the full line, vertical line, x equals -2, has a vertical asymptote at 1. Okay, so x equals 1, and also at x equals 3. And that came from the limits we found before. Okay, now that we've got the asymptote discussion out of the way, let's look at an example, right? I want to evaluate these following limits analytically. That basically means by hand. So this is going to be sort of our infinite limit cases. So as we see here, I'm going to look at the limit as x goes to 2 from the right of 1 minus 3x all over x minus 2. Now when we plug in 2, we get 0 in the denominator. Right? But in the numerator, right, we get 1 minus 3 times 2, so that's going to be -5. So that's not a 0 over a 0 case. In fact, this is a constant over 0 case. Squeeze that in there. That means that this limit is going to be plus or minus infinity. I know that, right? It's a one-sided limit. It's division by 0, constant division by 0, or constant divided by 0, I should say. I know it's going to be either positive or negative infinity. So really the question is, which one is it? Okay. Well, to check, what we basically do, all right, is we sort of, there are two ways you can do this. Okay, one way is to check the value. So let me real quick here rewrite this problem, tell you that it's going to be plus or minus infinity. Right, that much we know. And one thing we could do is check this value. So check 1 minus 3x over x minus 2 at some really close value to 2, right? At something really close to 2, but to the right of 2 or greater than 2, right? So maybe something like 2.0001, right? So that would be 1 minus 3 times 2.0001, and this would be 2.0001 minus 2. So might helps to have a calculator for this. So I got this is about negative 50,003. Okay? All right. So that means, well, we can probably guess this thing's going to negative infinity. That's a pretty damn big number and a pretty damn big negative number as far as shooting down to negative infinity. So I know which one it's going to be. So we can go up here, erase the plus and minus, put a minus. You have to check this. Okay, you have to. Another way to do this, and it uses a bit more logic, but one, you just pick a number, see if it works. Okay, see what you get. Pick a number really close to the value you're looking at on the right particular side. Another way you can do it, and there are a couple ways to write this. One that I'm fond of, right, is the following. Right, the numerator is not what's going to be the trouble, right? When you plug 2 into the numerator, this is going to be negative 5, right? No matter what happens, I mean, it's going to negative 5. Okay? It's the denominator that's really going to give us trouble, and what we basically have here is we're putting in a value's really close to 2, but greater than, right? Because if we think of our number line, here's 2. 2 from the right is coming this way, so we're looking again like at things like 2.0001, but no matter what, this guy here is positive. In fact, if I just plug in the 2 with the 2 plus, I kind of like to do that because this tells me that it's something like, right, something like 2.001, meaning that this piece is positive. That's what I really need to know. So I have, no matter what my x's are, I'm getting closer and closer to 2, obviously, with x. But this piece up here is negative. This piece down here is positive, meaning that the whole thing is negative, right? A negative over a positive. Right? So those are the two different ways you can actually do this. Either checking or picking or using logic and deciding where your positives and negatives are. Okay. Let's do the other example that was given to us, which was pretty much the same exact problem except from the other side. So this is asking us about the limit as x goes to 2 from the negative side of 1 minus 3x over x minus 2. And so once again, when we plug 2 in directly, we get negative 5 over 0. Right? So I know it's going to give us a plus or minus infinity. So let's do the checking method. So I'm going to check at x equals. Now, here we're looking at, here's 2, and we're coming at it from the negative side. Here's 1, so these are going to be things like 1.999. So let's check there, 1.999. Now, there's some people who will try and pick things like 1.5. Wrong. You've got to get really close, right? You've got to get really, really close. And that's kind of the unfortunate part about this is we want to get really close. So let's get even closer just to make sure, all right? Because you've got to make sure you're close enough to actually get the blow up. So this will be 1 minus 3 times 1.9999 all over 1.9999 minus 2. And use a handy calculator for these. And I get that this is 49,997. Okay, that's a big, big number, so it's clear that this guy is going to positive infinity. Okay, we get a positive number out. Yes, I do like to write positive for these problems. Early on, you know, once you leave this class, I kind of don't care what you do, right? But as you're learning things to help reinforce what's going on, that you have to check, right? You have to write me something here. Okay. The other option is with just using our logic, right? That the numerator is just going to go to negative 5, whereas the denominator is 2 negative minus 2. And this guy, no matter what x we choose, that is basically less than 2. Okay. So this whole thing here is going to be negative because I have some number less than 2, and I'm subtracting out 2. So I'm going to get a negative on the bottom, and we still have a negative on the top, meaning we have a positive all around. Okay. So, there are 2 different ways to do this problem. I don't care which one you do, but you've got to write me something. Either show the fact that you're plugging things in, or write a little message. You've got to tell me that you know what the sign of each piece is. Don't just put the answer, because I won't know how you got it. And that's what's important. Not just getting the answer, but showing me why your answer is correct. Okay, because keep in mind, it may not be, but if your explanation is correct, then I'm going to give you points. Enough? Okay, let's look at another example. Okay, so for our next example, what we're going to do is we're going to consider this function x squared minus 3x plus 2 all over x squared minus 1. So part A wants us to just look at the limit as x goes to 1, the two-sided limit here. So let's just go ahead and write that here. That will be the limit as x goes to 1 of x squared minus 3x plus 2 over x squared minus 1. And when we go to plug in 1, right, well, we definitely get 0 in the denominator, right, because we'll get 1 minus 1. How about the numerator? Well, we get 1 squared, so 1 minus 3 plus 2. So this is a 0 over 0 case, right? So we need to factor. Well, that's what we should probably start to do. 0 over 0 means more work. Right? So let's go ahead and try and factor if we can. Well, I definitely see right off the bat that the denominator factors the difference of squares, so that will be x plus 1 times x minus 1. And then the numerator, that's x squared minus 3x plus 2. I would want factors of 2 that sum up to be negative 3, so that is x minus 2 times x minus 1. And so the x minus 1's cancel. Okay, and we get the limit as x goes to 1 of x minus 2 over x plus 1. Now we can just plug in 1, right? Because we won't get division by 0 anymore, so that would be 1 minus 2 over 1 plus 1, just to get it explicitly. So we get negative 1/2. So this is a place where f is undefined, but its limit exists. Okay, that's basically meaning that we're going to have like a hole there. Right? Now, if we check the limit as x goes to negative 1 from the right, well, let's go ahead and just rewrite this problem here. Be the limit as x goes to negative 1 from the right of x squared minus 3x plus 2 all over x squared minus 1. Now, if I plug in negative 1, well, I'm going to get 0 in the denominator again, right? Because, well, x negative 1 squared is going to be 1, so I'll get 0 down here. And then in the numerator, if I plug in negative 1, well, I'm going to get 1 plus 3 plus 2. So this actually ends up being 5. Okay. Right, so this is a constant over 0 case. And what does that mean? That means it's definitely a plus or minus infinity. Now, one thing I want to do before we move on is, since we can factor and cancel like we did previously, I'm going to do that again. Right? I'm going to simplify the problem and instead look at this limit. The limit as x goes to negative 1 from the right, x minus 2 over x plus 1. Okay? It's going to make things way simpler, because now when we plug in negative 1, this of course goes to 0. Now when we plug in negative 1 from the right, this is going to negative 3. Okay? Does it really matter all that much that these are going to different numbers? Not really, because remember, since this is a constant over 0, this is going to be plus or minus infinity. What this number up top is doesn't really matter that much in the long run. Okay? So we have the two ways to go about doing this. Negative 1 from the right, and negative 1 from the positive side. So that's going to be things like negative 0.999. Okay? So let's check at x equals negative 0.999. Okay? Hopefully that's close enough, but say negative 0.999 minus 2 over negative 0.999 plus 1. And you can probably just see from here exactly what's going to happen, like doing a mixture of both versions, because this is going to be negative. Right, this will be negative 2.999. And this is going to be positive because I have 1 and I'm subtracting 0.999. Right? So this is negative 2. Well, I'll just write it out. This is negative 2.999. Right? And this is going to be positive because it's 1 minus something less than 1, which is 0.001, and if I plug that in, I get negative 2,999, so about negative 3,000. That's pretty good. If we'd gotten something, maybe 4 nines, we would have probably gotten closer, but the important part is negative infinity. Okay. The other way you could do this, of course, is if we have the limit as x goes to negative 1 from the right, x minus 2, or x plus 1. Well, the numerator, of course, is going to negative 3. The denominator, I have negative 1 from the right plus 1. Again, this is a little tougher to do the logical way, but remember, this is something like negative 0.999, so this whole thing here is positive, whereas the top is negative. Okay. Another way I like to write this, of course, is since this is positive, I could write this as negative 3 over 0 positive, right? 0 from the positive side. Because if this whole thing is positive, this thing is getting closer and closer and closer to 0, but from the positive side, so the whole thing ends up being negative infinity. All right, the next example, or the next problem asked us to look at the same thing, but from the other side. Okay, so let's do that real quick. Say we look at the limit as x goes to negative 1 from the negative side of x minus 2 over x plus 1. Again, I'm jumping right to the factored version because, well, that's the most useful one. And once again, okay, this is going to be 0, or division by 0, so negative 3 over 0. So we know it's going to be plus or minus infinity. Now, negative 1, right, from the left side, this is going to be things like negative 1.001. So we'll check something like that. Negative 1.001. So negative 1.001 minus 2 over negative 1.001 plus 1. And we can see here that this is going to end up being something negative, right? Because I have 1 minus something greater than 1, so the denominator is going to be negative. But go ahead and crank this out. Okay, and I got that that is 3,001. Okay. Meaning that we get positive. Right, so this limit is going to positive infinity. And again, the other way you can check this is using logic. It's a little tougher on this example, as I said, but again, the top is going to go to negative 3. The bottom, well, this is negative 1 from the negative side plus 1. And again, these are things like negative 1.001. So we're actually subtracting something larger than 1 when we do this. So this whole thing here is going to be negative. Okay, so that means this is actually going to negative 3 over 0 from the negative side. Okay. which gives me, well, negative, negative, positive infinity. Okay, so that adds one more thing to our list of limit strategies. Okay, so the limit strategies right? If you get a constant over 0, right, then the limit of that, whether it's from the right or the left or both sides, you have to check both sides. For example, here we got positive infinity from one side, negative infinity from the other side. So the two-sided limit as x goes to -1 of x minus 2 over x plus 1 does not exist. Right, so if you are asked for a two-sided limit, you actually have to check both sides in this case. Right, so in this case, we know that it's a plus or minus infinity, but you have to check. Okay? That's the key here. Right? Don't just put infinity, don't just put negative infinity. I'll have no idea how you know that that's the right one. You've got to write something to tell me that you know that it's correct. All right, and that's pretty much it for 2.4. Next we'll be looking at 2.5, which is limits at infinity. So here, instead of here, we were looking at when x goes to a number, f goes to infinity. Next up is basically, okay, what happens to the function if x goes to infinity instead. So stay tuned.